All right, so we're going to look at how to convert a vector equation to Cartesian equation in 2 dimensions. So some of the background knowledge you'll need to know for this is about unit vectors. A unit vector in the x direction is basically what we call I, unit vector I, and it is a vector from the origin to the point 1, 0. And similarly, in the vertical direction, we call that unit vector j. It goes from 0 to 1. So if we look at an example here, let's talk about a certain combination of these vectors. So we're going to call some vector r, which is equal to vector I plus 5 groups of vector j plus t groups of I plus 2j. So this is just an example. Remember that this t is a parameter, and this parameter is what varies the where the endpoint of this vector r is. So it'll make more sense as we step it out. If we have t equaling 0 to begin with, we're just going to get I plus 5j. So some more background information you need to know here is a little bit about vector addition. So I'm going to basically take vector I plus 5 groups of j, 1, 2, 3, 4, 5. So a bit of vector addition there. And that's going to get us to this vector at the moment. So when t is 0, we get this vector that's at the point P here, because this whole thing just disappears, right? But then as we change the values of t, this thing comes into play a little bit. And let's just show you what that looks like. As we change t, we can see that that point P traces out. Hopefully what you can see is a linear line. It might be a bit hard to see that it's on a linear line, but I can guarantee you that it is. If we just put that back to there for now, we can see that the vector r, this thing, is just equal to the vector pointing to the point 1, 5. Okay, what we're going to do is we're going to convert this to a Cartesian equation. We want to know what is the equation of the line. So what we can do is we can expand this t in. So just using the distributive law, you can expand the t in. So you get t multiplied by I plus 2t multiplied by j. And then we're just going to move things around a bit, get the I vectors together and get the j vectors together. So we get r equals I plus ti plus 5j plus 2tj. Okay, let's take out I, the vector I, as a common factor of the first part. So we'll be left with 1 plus ti. So that's our vector in the x direction. And similarly here, take out j as a factor, and you're left with 5 plus 2t. And so what you would say is, all right, 1 plus t is the amount that we're moving in the x direction, 5 plus 2t is the amount that we're moving in the y direction. So we can actually equate these to our x values in Cartesian coordinates or in Cartesian form. So we'd say that x equals 1 plus t. Okay, and so what we can do now is we can rearrange for t and then eliminate t so we can find the equation of the line. So stay with me, and what we'll do is we'll just rearrange this for t. So we get t equals x minus 1, just rearranging that. Okay, we also know that y equals 5 plus 2t. We know that t now is x minus 1. So we substitute in, wherever there's a t, we put x minus 1. And expanding that, you get 5 plus 2x minus 2. 5 minus 2 is positive 3. Positive 3, not negative 3. And yeah, so you have a 2x plus 3 if you just expand this out. And lo and behold, if we graph this line here, this pink line is 2x plus 3. If you think back to linear relation, it's got a y-intercept of 3 and it's got a gradient of 2. And so you can see that that point P very neatly travels out points on the line 2x plus 3. So that is how we convert between a vector equation to a Cartesian equation in 2 dimensions. What we'll talk about later is when you have to do it in 3 dimensions, which is a fair bit more challenging, but hopefully that made some sense and you found that useful, and good luck with all your studies.